And the recording is going now as we speak. I'll wait a few more seconds before discussing anything of substance. We'll wait until the top of the hour. Okay, welcome everybody to College Geometry, class number 9. I hope everybody had a very happy Thanksgiving, and I want to wish everybody a happy holiday season. I hope you all spend time with your family and do your schoolwork. Alright, not necessarily in that order. Okay, thank you very much, appreciate it. It is time for a new subject, a subject that we really haven't covered yet much in this course, and that is the subject of ratio and proportion, which as it leads to similar polygons. Until now we've been discussing equality or congruence, now we are going to discuss similarity. Well, first of all, you need to know what a ratio and a proportion are. A ratio means, well, according to the slide, it's an ordered pair. It should be ratio, not ration. But anyway, an ordered pair of numbers that reflects a mathematical relationship between them. A to B, A colon B, A divided by B, either way would be considered a ratio. If, for example, there is a 5-to-3 ratio of one quantity to another ratio quantity. For example, if I have, let's say, $5 for every $3 that you have, that of course means that if I have $50, then you have $30. Ratios is a numerical relationship. When you're talking about geometry, or when you're talking about algebra, or when you're talking about a word problem, ratios are very often expressed with regard to with variables. For example, if I have a triangle and I tell you that side AB has a ratio of 4-to-3 to BC, in other words, I say AB to BC has a ratio of 4-to-3. We don't know what that is. One could be 4, one could be 3, one could be 16, the other could be 12, one could be 400, the other could be 300, one could be 1200, the other could be 900. We just know that the ratio is 4-to-3. So the way we can express this with a variable is we can say AB is 4x and BC is 3x. In other words, whatever x is, it's the same or it's consistent between AB and BC. So for example, if AB is 12 and BC is 9, then x would be 3. If AB is 400 and BC is 300, then x would be 100. Either way, when you're talking about a ratio, you can express them as with a variable. That leads us to a proportion. A proportion is really just a pair of ratios. A proportion is, let's say, for example, 4:3, divided by is the method that is used in a proportion, as, let's say, 400:300. Now, is this a true statement? That 4:3 as 400:300? Well, the answer, of course, is yes. The things on the opposite sides of the equal sign are, of course, equal. The question becomes, what happens if you're not sure what one of the quantities are? For example, if I tell you that 5 is to 12 as x is to 60, and I figure out what x is, well, the way to do this from an algebraic perspective, and again, so far this is not really based on geometry, this is really an algebraic issue, the way to figure this out is to cross multiply. You do the x times 12 equals the 5 times. So let's say x times 12, 12x equals 5 times 60, which is 100. Then you can divide each side by 12 to isolate the x. And so you've got x equals 300 divided by 12, which in this case is 25. So, is this a true statement, by the way? 5 is to 12 as 25 is to 60? Well, it better be a true statement, because this method should definitely work. And of course it is. If you divided each side by 5 of the fraction on the right, you would get 5/12. So generally speaking, that is the way to establish a proportion, to solve a proportion. One of the things that is a practical, everyday use for this, that the book plays up a lot is using a map that is drawn to scale. Now, I think we discussed this earlier in the course a little bit. Everybody remember what a map is? You know, it's before they had GPSs and phones that did the GPS for you. Okay, hopefully you'll remember what a map is. In the old days, back before they had GPSs and before they had smartphones, if you wanted to know where you were going, you would take out a piece of paper, and the piece of paper would have a rendering of the place you were going to and the place you were at, and you would look and you would say, and it would, in the bottom left-hand corner of the map, and they still have these, of course, it would say something like 1 centimeter equals 5 miles. You know, you'd have a road map, and so it would tell you how far you would be able to figure out how far you are away. Now, let's say you take your ruler and you figure out that the place you're going to is 7.5 centimeters away from the place that you are. How would you figure out how many miles it is? Well, of course, you would just multiply by 7.5. But from a proportion perspective, what that is, well, 1 centimeter is to 5 miles, because 1 centimeter is 5 miles, as 7.5 centimeters is to x miles. Do you see why that is? That is the proportion that applies in this case. 1 is to 5 because 1 centimeter is to 5 miles, as 7.5 centimeters is to x miles. And there you would cross multiply. 1 times x is x, and then 7.5 times 5 is 37.5. So you're 37.5 miles away. Now, if you have 1 centimeter, of course, it's a little bit easier. If you have a different number, then of course it becomes a little bit more complex, although not much. It really is not too complex no matter what proportion you use. But for example, if you say 2.7 centimeters equals 4.8 miles, let's say you have like a weird map. And instead of saying 1 centimeter equals 5 miles, your map says 2.7 centimeters equals 4.8 miles. Well, it's just as easy. So if you find out that you're 7.5 centimeters away, that's no problem. Just do the same proportion. 2.7 is to 4.8, as 7.5 centimeters is to x number of miles. So you'd cross multiply and you'd get 2.7x equals 7.5 times 4.8. Now this, I hope you don't mind, I'm going to do it on a calculator. 7.5 times 4.8. Not that I can't do it in my head, but I want to get it right. It comes out to 36. So you would divide each side by 2.7 to isolate the x. And you would get 13 1/3. So you would have, so based on that, you would be 13 1/3 miles away. That's generally speaking how to do a proportion. Okay, now let's apply this to geometry. Before we do that, one more thing, and one more concept, really the same thing as a proportion. This is really a special type of proportion, and that is the arithmetic mean. An arithmetic mean applies when the same value is in the middle of the proportion. The example on the slide over here, AB equal A is to B as B is to C. If A is to B as B is to C, well, that means A over B equals B over C. That means when you cross multiply, you have B times B, which is B squared, equals A times C. So in that case, you would simply, you just figure this out based on whatever numbers you have. Here's an example. I think I have an example over here next. Yeah, okay, here's an example of a mean proportion. It's really just a type of proportion, but I'm discussing it over here because it has a practical application. There is a rule in geometry, a theorem in geometry actually, that the altitude of the hypotenuse of a right triangle to the other side, from the right angle to the hypotenuse, is the mean proportion between the two parts of the hypotenuse that it breaks up. So, in this example over here, ABC is a right triangle. By the way, how do you know that ABC is a right triangle? Just by looking at the diagram. What tells you that ABC is a right triangle? Well, yeah, exactly. There's that right angle side. Well, not D actually. D is not the big triangle. ABC is the big triangle. Angle A or CAB is a right angle. It has that little right angle marker. So CAB is the big triangle. X, which is AD, is an altitude of the triangle. An altitude of a triangle means a line that goes from one angle to the other side, measuring a right angle. So over here, ABC is a right triangle. That's first of all. ABC is a right triangle. And AD is an altitude. An altitude means a line from one angle to the other side, measuring it at a right angle. In such a case, the rule is that the altitude is the mean proportion between the sides. So if I were writing a proportion, how would I write that? What would my proportion be? X, in this case, which is the altitude, is the mean proportion between 9 and 4. In this example, the B would be X. So the way I would write that is I would say 4 is to X as X is to 9. Or, of course, I could write it like this: 9 is to X as X is to 4. It doesn't matter. It's the same. It's going to come up with the same answer either way. But the point is, X is the mean proportional between the two sides of the hypotenuse. ABC, of course, by the way, is the hypotenuse. Because in the big triangle, in other words, triangle ABC, this is the right angle, CAB is the 90-degree angle. So therefore, BC is the hypotenuse. Okay? So X, or AD, is the mean proportional between CD and DB. So, how would we figure out what X is? What should we do first? Let's say we're taking this one over here. What should we do first? Let's cross multiply. Okay. So X times X is, of course, X squared equals 4 times 9, which is 36. By the way, again, I know we didn't cover a lot of algebra earlier, but hopefully you all realize. Does everybody realize why X times X is X squared and not 2X? How do I get 2X, by the way? Let's say I've just got 2X's and I want to get 2X. That's X plus X. When you multiply two variables, you add their exponents. So X times X is X squared because the exponent of this X is 1, and the exponent of this X is 1. That's the default rule. So X times X is X squared equals 36. And in order to isolate X, you take the square root of each side in order to get X all by itself. And so you take the square root of 36. Now, of course, the answer really is plus or minus 6, because the square root of 36 could be positive 6 or negative 6. Either one multiply up to 36 when you square it. However, since it's geometry and since you're talking about lengths, you reject the negative value and you have X equals 6. So in this example, X would equal 6, and you'd have a 6 over here. By the way, then can we figure out AC and AB? How would we figure out AC and AB? Anybody have any suggestions if we wanted to figure out AC and AB? Well, how about using the Pythagorean theorem? We've got two little right triangles in there. Yeah, we can use either of the two smaller right triangles. Let's say we wanted AC. Well, if we wanted AC, well, AC is the hypotenuse of the right triangle ACD. So we could say 6 squared plus 9 squared equals X squared, because A squared plus B squared equals C squared. That's this side and this side are the two legs. So 6 squared is 36, plus 9 squared is 81, equals X squared. That means X squared equals 117. So X is the square root of 117. What's the square root of 117? It's a little under a little under 11, probably about 10.8 or so. Anybody have a calculator with square roots? What, 117? Yeah, about 10.8. A little about this. So this is going to be about 10.8. And AB, how would we get AB, by the way? There are two ways we can get AB. We can get AB because it's the hypotenuse of the right triangle ABD, or because it's a leg of the right triangle ABC. Let's do them both and make sure that we get that we get the same answer. That's obviously important. If we get different answers, then it would mean there's something seriously wrong. But I'll do it on the bigger page over here. AB, let's do it first as a leg of the triangle ABC. So that would mean a squared plus b squared equals c squared. Now, AC, or AB we'll call x, plus AC, which was the square root of 117 squared, equals c squared, which is, what was it, 9 plus 4 is 13, equals 13 squared. So this would be x squared plus 117, because that's the square root of 117 squared is 117, equals 169. Divide, subtract 117 from each side, and you have x squared equals 52. This equals the square root of 52, and the square root of 52 is, again, a little bit over 7, approximately 7.2 or 7.1, something like that. Again, if I do it on my calculator, yeah, but a little over 7.2. Okay, that's how to do it one way. Well, now let's do it the other way. Let's do it as the hypotenuse of triangle ADB. Same thing. Well, here we've got a squared is plus b squared plus c squared equals 6 and 4 are the legs. So you got 4 squared plus 6 squared, whoops, equals x squared, which is AB. 4 squared is 16, plus 6 squared is 36 equals x squared. 16 plus 36 is 52 equals x. Of course, means that x is the square root of 52. So either way, you'd get the same answer. Obviously, you have to get the same answer because you're just using the Pythagorean theorem on two different triangles. Okay. Does anybody have any questions on that, by the way? Or would like me to go over it? And I know I did that relatively quickly, but hopefully everybody was able to get that. And if you have any questions or would like me to go over something again, please feel free to let me know. Now we get to similar triangles. A similar triangle works as follows. Pairs of triangles are similar if their angles are the same, and the rule, the ramification of that, is that the lengths are in proportion. As you can see from the diagram over here, we've got two triangles over here. Their angles are the same. Now, we don't know that, but I'm telling you that their angles are the same. And their sides are in proportion, which means the one on the left is 3 and 4, whereas the one on the right is 6 and 8. And those, of course, are in proportion. By the way, what's the hypotenuse of the small triangle at the bottom? Can anybody tell me what the hypotenuse of the small triangle? It's 5, right? Why 5? Because it's a 3, 4, 5 triangle. And what about the big one? What's the big hypotenuse? 10. That's right. Well, for two reasons. It's also a 3, 4, 5 triangle, but also because it's proportional to the other one. It's proportional to the smaller one. Of course, you could also use the Pythagorean theorem. 3 squared plus 4 squared is 3 squared is 9 plus 4 squared is 16. That's 25. So the square root of 25 is 5. And of the big one, 6 squared is 36. 8 squared is 64. 36 plus 64 is 100. Square root of 100 is 10. So that's what similar triangles mean. So the next question is, how do you know that two triangles are similar to each other? And the answer is actually very similar to the rules for congruence. Remember, when you were talking about congruence, you had, let's put it over here. let's make congruence and similarity. Okay. For congruence, for example, you had, if all three sides were equal to each other, so you had side, side, side is congruent to side, side, side. Now, the same thing is true with similarity, except not equal to each other, but if they're in proportion. If all three sides are in proportion to each other, that proves that the two triangles are similar. By the way, for similarity, you use the squiggle without the equal sign. The equal sign with the squiggle is congruent, which means exactly equal to each other, whereas similar means you just use the squiggly thing. So if the three sides are in proportion, then the triangles are similar. So if I have two triangles, and I say, let's say, for example, this is 4, and this is 3, and this is, let's say, 4 also. And let's say, so this is 10, and that's 10, and that's 7.5. Are these two triangles similar to each other? What do you think? They're in proportion, right? The one on the right is simply 2.5 times the size as the one on the left. 7.5 is 2.5 times the size of 3, and 10 is 2.5 times the size of 4. Okay, if the angles are equal, for congruence you didn't have AAA. AAA didn't work at all. But for similarity, you have all three angles are equal to each other. Then the triangles, if the angles are equal to each other, then they are similar. The two are similar to each other. And because three angles work, then two angles work also. Because remember, a triangle has to equal 180 degrees altogether. So if two angles are equal to each other, so by definition, the third angle also has to be equal to each other. So if I've got two triangles like this, let's say A, B, C, and D, E, F. And I tell you that angle F is 40 degrees and angle C is 40 degrees. Do I know that these two triangles are similar at this point? Not yet, because they could have different angles than the other two. But now let's say I tell you that angle D is 80 and angle A is 80. Now, are these two triangles definitely similar to each other? The answer, of course, is yes. What are angles B and E, by the way? What do you think? What are angles B and E? Hello? Okay. 60, that's right. Why are they 60? They have to equal to 180. Very good. And the 80 and 40 are 120 altogether. So that leaves over 60 remaining. Okay, so these, of course, have to be similar to each other, which means that if I tell you that this is 5 and that's 10, and let's say I tell you that this is 7, so what does EF have to be? $14. That's right. Very good. And what if I tell you that AC is 6? Then what does DF have to be? 12. Because the theme is that they're doubles. And the same thing is true also with SAS. SAS, just like congruence, you had SAS is congruent to SAS. If you have a side in proportion and then an angle that's equal in the middle, in other words, you have two sides in proportion, okay, like this, and an angle in the middle, like you have on the diagram over there on the bottom of the slide, these two triangles have to be similar. Very similar to congruence. Over there, 2 and 4 are, of course, in proportion with 3 and 6. And because the angle between them is similar, so the two triangles have to be similar to each other. Let me ask you a question. What if I told you that this was 5? How much would this one have to be? The other one. Okay. 7.5, right? It's 7.5. Why is it 7.5? Because if you look at the ratio of the 2 to 5, that's the same as the ratio of this to this. So 5 is 2.5 times 2, so 7.5 is 2.5 times 3. And of course, because the triangles are similar, all the angles are equal. So if I told you this angle was 30 degrees, then that angle has to be 30 degrees. If I told you this angle was 40 degrees, then that angle has to be 40 degrees. And then the third angle is whatever 180 minus the rest of it is. Okay, that is proving similarity. Another aspect of similarity is when you have two triangles that are overlapping, like this, where two lines are parallel and share a third angle, the two triangles that you see in this diagram have to be equal. Or have to be, not equal, I'm sorry, have to be similar. This triangle, sorry for my sloppy drawing here. 1 second. I think you can, okay. Well, anyway, this whole triangle here has to be equal to the entire big triangle. Why is that, by the way? Who can articulate why that is? Why the small triangle, the triangle on top, has to be equal to the big triangle? Well, let's figure this out. Do they share any angles? Are there any angles that we know are equal to each other? Well, the answer, of course, let's give them all letters so that we can figure. Let's give all the points letters. Let's call this A, this point B, this point C, this point D, this point E. Okay. So angle A, first of all, is of course equal to itself. And angle A is an angle in both triangles. We want to prove that triangle ABD is similar to triangle ACE. Well, first of all, they both share angle A. Do you see why that is? You see why angle A is shared between them? It's part of the smaller triangle, ABD. It's also part of the bigger triangle, ACE. Okay. What about angles 1 and 2? What is the relationship between angles 1 and 2? They're equal to each other. Why are they equal to each other? Remember that BD and CE are parallel lines. They have those little arrows, which signifies that they're parallel. Well, let's break this down a step further. Let's do a little helper angle in the middle. Let's do angle 3. What is the relationship between 1 and 3? The relationship between 1 and 3 is that they're supplementary, which means they equal up to 180. Why? Because they're consecutive angles surrounded by two parallel lines. Whenever you have two parallel lines and are cut by a transversal, consecutive angles are supplementary. So angle 1 and angle 3 are supplementary. What about angles 2 and 3? What's their relationship? They're also supplementary. Why? Why are angles 2 and 3 supplementary? Who can tell me why angles 2 and 3 are supplementary? Okay, because they equal 180, and the reason is because they're a linear pair, right? They're on the same line. Two angles on a line that together make up a line equal 180 degrees. Okay, so because of that, because 1 and 3 are 180 and 2 or 3 are 180, so obviously angle 1 equals angle 2. So if angle 1 equals angle 2, so now we've already got two lines, and of course this line, these two angles are equal for the exact same reason. So now we've got A is equal to itself, we've got 1 is equal to 2, and we've got, let's say, 3 is equal to 4. So for that reason, the two triangles are similar to each other. Okay. The next theorem, which is really just the same, it's just a corollary to the one we just discussed. There's really no distinction between this and what we just discussed. And that is the midsegment of a triangle is parallel to the third side and half of its length. A midsegment means a segment that joins the midpoint of the two sides. So if AD is equal to DC and CE is equal to EB, well, first of all, the two triangles are similar for the same reason we discussed before. This triangle is similar to the entire triangle ABC. And because of that, if the sides, of course, are in proportion. So CD has to be 1/2 of CA, and CE has to be 1/2 of CB. It's really just a corollary to what we just discussed. Okay. And finally, we've got the mid-quad theorem. This is in the book. It's an interesting theorem, just something to remember. And the idea is any quadrilateral, doesn't matter what the quadrilateral looks like. The ABCD quadrilateral is meant to look a little weird. It's not ABCD is not a parallelogram. It's not a rectangle. It's not a trapezoid. It's not a square. It's nothing. It's just a random quadrilateral with random points. And if you draw the midpoints of all four sides, you have to get a parallelogram. So if I draw the weirdest quadrilateral I can draw, okay, that's a really weird quadrilateral. Let me draw another one. Okay, that's a quadrilateral. It actually looks a little like a trapezoid, but let's assume it's not a trapezoid. If I take the midpoints of all four sides, let's change the colors a little bit here. So I take the midpoint of this side, the midpoint of this side, the midpoint of this side, and the midpoint of this side, and I draw all four midpoints. This has to be a parallelogram. Now, it doesn't really look like a parallelogram because my drawing isn't very good, but although it looks kind of a little like a parallelogram. The one on the slide, I think, is a lot better looking. The one on the slide shows that even though ABCD is just some kind of a weird warped quadrilateral, MNPQ has to be a parallelogram, assuming that M is the midpoint between AD, N has to be the midpoint between AB, P has to be the midpoint between BC, and Q has to be the midpoint of CD. Okay. So with that in mind, those are some of the rules. And now we're going to get down to some problems over here. This time, rather than having to use Paint like we did last time, this time I downloaded an entire PDF full of samples. And this one, I'd like everybody's help. Hopefully we can get everybody involved over here, okay? Everybody ready to go? Everybody ready to help me? All right. There we go. Okay. All right, okay. The triangles shown below are similar. Find the exact values of A and B. Now again, there is no A in number 1, but what's the value of B? This is a very easy one, but how would we figure it out? How would we figure out what B is? Did anybody tell me? Well, if the A and B are similar, and they are, of course, because the angles are similar. The angles are the same, alpha, beta, and gamma. You have alpha over here is equal to alpha over here. It's the same letter, which signifies that they're equal to each other. And then you've got beta. Oh, no, 1 second. What did I do here? Okay, beta is equal to beta, gamma is equal to gamma. Fine. Anyway, so B, how would we figure out B? Well, it has to be along the same proportion. So we know that these two are in proportion, and these two are, well, these two are in proportion with the bottom two. So we could say 5 is to 7 as 4 is to x. See how we did that? So once we do that, once we establish that ratio, now we can simply cross multiply. Let me use a thinner pencil so it'll be a little easier to write. So we cross multiply. 5 times x is 5x. Well, 1 second, how do I do that? All right, anyway, we're going to have to use this. 5x equals 7 times 4, which is 28. Divide each side by 5. And if you divide 28 by 5, you get x equals 5.6. So B would be 5.6. How about A? How would we figure out A? How would we figure that out? Same way. Same exact way. We could either use the 4 and the 5.6 ratio, or we could use the 5 and the 7 ratio. It's the same ratio, obviously. But either, so let's use the 5 and the 7. It's a little cleaner. So 5 is to 7 as what? As A is to 8. Because 5, 7, 8, 8. That's the same ratio because the two triangles are similar. Let's cross multiply. 7 times A is 7A equals 5 times 8, which is 40. Then divide each side by 7. And A equals 40 divided by 7, which is 5 and 5/7. 5 and 5/7 is about, what's 5/7? About 72, about 5.72, approximately 5.72. Okay. How about number 2? Consider the picture below. Let's scroll down a little bit here. Okay. All right. We've got two triangles here. And we've got, by the way, okay, first of all, let's take A first. Use the Pythagorean theorem to find out the value of A. How do we do that? How do we use the Pythagorean theorem to find out the value of A? Well, we've got two sides of it, right? We can use it. What's the Pythagorean theorem? Remember the Pythagorean theorem? The Pythagorean theorem was a squared plus b squared equals c squared. So the sides are 5 and 12. So it would be 5 squared plus 12 squared equals c squared. 5 squared is 25 plus 12 squared is 144 equals c squared. That's 169 equals c squared. So and the square root of 169 is 13. Hopefully you could have also remembered that it's a 5, 12, 13 triangle. If you remembered that, then it would have been really easy. But if you didn't remember it, you could always just use the Pythagorean theorem. So that's 13. Okay. Now, prove that triangle ABE, that's the small one, and ACD, I don't know why it's not letting me underline this thing. For some reason it's not. Huh, it's weird. Okay. There we go. Now, why is this not working? Huh. Okay. Sorry about that. Okay. Sorry, this is getting a little messy here. All right. Prove that triangles ABE and ACD are similar. Why are they similar? Who can tell me in English why they're similar? We're not going to sit here and prove the whole thing, but why are they similar? How do we know they're similar to each other? ABE, that's the small triangle, and ACD, which is the big triangle. Why are they similar to each other? Okay, I mean, there are many reasons. One is ASA. Okay, that's true also. That's true. I mean, what I was thinking of is we know that this angle and this angle are equal because they're both right angles, and we know that angle A is equal itself from the reflexive property. So that means they've got two angles equal to each other, and once they've got two angles equal to each other, you know the third one also has to be equal to each other. So by definition, the two triangles have to be similar. So based on the fact that they're similar, what is x? What's the value of x? Well, what's the ratio between AB and AC? It's half, right? AB is half as long as AC because they're 12 and 12 altogether, which means the other sides also have to be in proportion, which means BE has to be half as long as CD, and BE is 5, so CD has to be 10. So what's B? By the same logic, they all have to be in proportion. So that also has to be 13, exactly, because the hypotenuse has to be the same thing. And there are many different ways you could have done it. You could have used the Pythagorean theorem. You could have used the big triangle as being a 5, 12, 13 triangle. But the easiest way to do it is to simply remember that they're in proportion. So just like the bottom was 12 and 12, the top has to be equal to, so the top has to be 12 and 13. Okay, number 3. A person is standing 40 feet away from a streetlight that is 30 feet tall. How tall is his shadow? How tall is he, excuse me, if his shadow is 10 feet long? Can we set up a proportion to do number 3? Let's do number 3 over here. What would our proportion be? What's the ratio that we know of from the streetlight? And how does that apply to the person? Well, we know the ratio is standing 40 feet away from a light that's 30 feet tall. So let's say 40 is to 30. We're using the ratio of feet away to feet tall. So that equals, well, we don't know how tall the person is. So for the tall part, we'll use x. And for the away part, that's really the long part, we'll use 10. See why that we established that ratio? This was the length to height ratio, was 40 to 30. So for the person, it's the same thing. The person, the height to length ratio is 10 to x. So now we can simply cross multiply. And we've got 40x, cross multiply, 40 times x equals 30 times 10, which is 300. Divide by 40. And x equals 7.5. So this is a person that's 7.5 feet tall. I don't know why the people who wrote this decided to make this person like a basketball center or one of the tallest players in the history of the world, I guess. But this person happens to be 7.5 feet tall because it's the same ratio as 40 to 30. Okay, let's try B. B, you're gonna help me with, because B is really the same exact problem, except being slightly different. A 6-foot tall person is standing 24 feet away from a streetlight that's 15 foot tall. How long is her shadow? Okay, let's start. Let's do B, because B is really essentially the same problem. Either way, what we're trying to do is we're trying to set up a ratio that corresponds each side's values. So in 3A, it told us the ratio of the streetlights. Again, we're assuming that the ratio of height to distance is the same. I mean, that's true. Anybody ever read The Mysterious Island? Well, because that's how long it would project. That's how, in other words, that's how far, based on, a light based on its angle projects a certain way. Anybody ever read The Mysterious Island by Jules Verne? At one point, they're stuck on this island. It's kind of, by the same author as 20,000 Leagues Under the Sea. And if you've never read it, it's a classic, by the way. You should read it. But anyway, at one point they want to figure out how far away a certain precipice is, how far a certain volcano is from them, and they can't measure it because there's all sorts of rocks and obstacles in the way. So what they do is they go out a certain time of the day and they measure their own shadows based on their own height, or they put up, or you can measure a ruler, you put up a 10-foot stick, you put up a 10-foot pole, and you realize that the pole is making a 4-foot shadow. So you look at if you see if a 10-foot pole makes a 4-foot shadow, so the ratio between the height and the shadow is 10 to 4. So now, if you can measure the shadow that the mountain is making, well then, by definition, you can figure out the height of the mountain. So it's a similar concept to 3. Let's look at 3b over here. A 6-foot tall person is standing 24 feet away from a street light that is 15 foot tall. How long is her shadow? So let's say the street light, no, the sun, why would the sun hit it differently? If it's the same time of day, then the sun's the sun's always is going to hit everything at the same angle. If it's a different time of the day, you're right. But if it's the same time of day that you're measuring, the sun is the same part of the sky. The sun's going to cast the same shadow. No, it's always going to, all shadows are going to be in the same direction. Try it. Go outside one day when it's a sunny day, and take a yardstick and take yourself. If you're 5.5 feet tall or whatever it is. No, but the shadow is going to be the same. Assuming the I mean, again, you don't have to make any assumptions. Every object is going to cast a shadow in the same direction. Put yourself and a stick next to each other, and unless you block out the light from the stick, obviously, if you block out the light from the stick, then the stick is not going to make any shadow because the light's going to be blocked out. But if you put a light next to you, if you have a 3-foot, let's just say for argument's sake you're 6 feet tall, and probably not that many people here that are 6 feet tall, but let's assume you're 6 feet tall, and you take a 3-foot stick, and you put the stick next to you. Both of your shadows are going to be in the same direction, and the stick shadow is going to be exactly half of your shadow, because the sun is hitting both of you from the same direction. Stick and making it so that they saw this. You see, it's very hard to describe. But they took the stick and looked at it, so that their eyes were looking straight at the top of the stick and over the top of the stick, straight to the top of the mountain. So they used the concept of a similar triangle to figure out the distances. I see. I'm having trouble explaining this. Let me get Microsoft Paint out and try to explain this because it's a fascinating. It's a fascinating thing. All right, just give me 1 second. Let me just. Okay, does everybody see my... Okay, good. All right, there we go. All right, so what they did in the Mysterious Island, let's say they had this tall mountain that was, like way up here, and this is a big volcano here. And there was a long ground, and they wanted to know how tall, and they were, let's say the people were standing here, and there was this really tall mountain on the other side. So what they did was they took like a stick and moved it far enough away from the person so that when they looked up, it was the same angle. So in other words, they made a stick. So let's say you could let's draw a line straight from the person's eyes to the top of the mountain. Let's say this is the person's viewpoint, straight to the top of the mountain. So they took a stick and put the stick far enough away so that the top of the stick was precisely in line with the mountain. See what I'm saying? They took whatever stick they had and they just moved the stick far enough away from the person so that the the line of sight went straight at the top of the stick to the top of the mountain. So now they could use the concept of similar triangles. Because if you look at the triangle that's, let's say the person over here, and then to over here, and this triangle here, let's say. Whoops. Okay, I didn't mean to make this. Well, anyway, this the big triangle, which includes this area over here and this whole thing, is similar to this triangle. I don't know. It's not, for some reason, it's not letting me just color in this area. But you'll have, so just trust me. So this angle, of course, the angle between the person's sight and the ground, let's say, is similar, is the same, and because obviously this is a right angle and this is a right angle, so these two triangles are similar. So the distance between here and here is proportional. Let's say, for example, this was 10 feet and this was 12 feet high. So if the distance from here to here was, 10 miles, well, then they know that the mountain is 12 miles high too. Again, they basically used this concept of similar triangles to figure out the height of the mountain. All right. Again, it's just an interesting little point that they used in the book. One second. How do I get this back open? All right. All right. Let's bring this back up. Okay. So let's go back to number 3 over here. A 6-foot-tall person is standing 24 feet away from a street light that's 15 foot tall. How long is her shadow? Well, okay. It tells us that from the street light, the ratio is 15 tall to 24 feet away. So we'll say 15 is to 24. So the ratio of the human is the same. The ratio of the human is 6 feet tall. So we'll put the 6 on top because it corresponds to the 15. And x is how long her shadow is. Could I draw this? Sure. A person is, let's say, 6 feet tall. Let's say 6. And is standing 24 feet away from the light. That is 15 feet. Where's the light? The light is over here. Okay, again, not much of a drawer, but that's okay. The light is 15 feet tall, and this is 24 feet away. So now how long of a shadow does that cast? Well, it's the same proportion. So 15 to 24, and this would be the shadow, so the shadow is x. 24 would be 6 is to x, 15 times x is 15x, 6 times 20 is, 140, and so it would be divided by 144, which would be a little under 10, 9 point whatever. Okay, let us scroll down a little bit and do number 5. So we don't have time. I don't think we're going to have time to do all of them. But let's do number 5. How would you do? Hmm. You know what? I'm not sure. I think that number 5 requires some trigonometry, which we didn't cover yet. 6 we can do. 6 we can do. How would you do number 6? Number 6, as we discussed before, one second. You know, this isn't working. I'll have to load it. Let me load this up over here. Okay, number 6. The picture below shows a right triangle. Find the length of the height h drawn to the hypotenuse. Now, this was the mean proportional rule. If you recall, the length of the hypotenuse, I'm sorry, the length of the altitude from the hypotenuse is the mean proportion between the two sides that it breaks up. So in this case, it would be 18 is to h as h is to 50. That's what the mean proportional means. So h times h is h squared. 18 times 50 is 900. And so you take the square root of each side, and h is the square root of 900, which is 30. So this would actually be 30. The h would actually be 30. Okay, let's take some of these practice problems here. Some of these should be relatively easy. Okay. For number 1, who can tell me the value of x? Let me make it a little bigger. You might not be able to see it so well. Who can tell me the value of x? It's in proportion, right? So what you would do is 9 is to 12 as x is to 5, right? Because they have to be in proportion. So you could say 9 over 12 equals x over 5, because the two triangles are similar. Then you'd cross multiply. Okay, 12x equals 9 times 5, which is 45. So x, divide each side by 12. And x is actually 4 and 1/12. 4 and 1/12 is the same thing as 4.12 or 1. Well, we'll just say 4 and 1/12. Close enough. Okay. What is no, 1 second, that doesn't make any sense. What did I mess up here? Did I say, yeah. Yeah, that doesn't make any sense. So what did I mess up here? 9 is to 12 as x is to 5. No, that's right. I'm sorry. I just didn't divide properly. Yeah, you're right. Okay, 45 divided by 12, which is 3.75. That's correct. Okay, good. So that's 3.75. Now, how would you figure out what y is? Well, now we could use the Pythagorean theorem, right? So if x is 3.75, then the Pythagorean theorem, which is a squared plus b squared equals c squared, 3.75 squared plus 9 squared equals x squared. Now 3.75 squared is, 1 second, 3.75 squared is 14.0625. We'll round it up to 14.06. Plus 9 is 81 equals x squared. So then you would add the 2. That would be 95.06. And the square root of that is a little under 10. It's actually, the square root actually happens to be approximately 9.75. So x is about 9.75. Actually, I think it's exactly 9.75. This, interestingly enough, the triangle on the right is also a 5, 12, 13 triangle. The triangle on the left is a 5, 12, 13 triangle. You can tell right away. So the triangle on the right is also if this is 13 over here, and this is 3.75, I believe this is exactly 9.75. It's in the same proportions. Okay. How would you figure out the value of a in the next one? We'll just look at the proportion. See, this is a little bit harder because first you have to find out the hypotenuse. Right, so first you'd have to find out the hypotenuse of the big one. Well, really there are two ways to do it. Number one, you could find out the side of the small one using the Pythagorean theorem, as Devore says, or you could find out the hypotenuse of the big one using the fact that it's a similar triangle. So you could say, for example, that this is, well, the 12 is to 36, well, that's 3 times, so the hypotenuse is 3 times 37. And 3 times 37 is 111. Okay, thank you. And then you could use the Pythagorean theorem to figure out what a is. You'd say 36 squared plus a squared equals 111 squared. And I don't know what you'd get, but you'd get something. I'll tell you what you would get. You'd get, I think, 105 actually. Yeah, okay, I think you'd get a to be about 105 if you use the Pythagorean theorem. All right, anyway, there are lots of these, as you can see. There's lots of practice over here. The homework has some of these, but the homework is also discusses trigonometric issues, which we're going to discuss next time. So I'm not going to look at any of the homeworks until after next class, because next class we're going to be looking at trigonometry. And a lot of these kinds of problems also require some trigonometry to solve. Trigonometry sounds complicated, but it's really not. I mean, the rules of trigonometry are just as easy as the rules as we've been discussing until now. So if anybody has any questions, please feel free to stick around. And I want to thank everybody for coming. And I'll see you all on Wednesday.